Hey guys, welcome to another lesson. So today we continue on with the topic of differential equations. So the first lesson we did, we explored the exponential growth and decay uninhibited. So that's unlimited growth and radioactive decay. And we also explored modified exponential growth and decay, which, the classic examples of heating up a turkey or heating up something frozen, or Newton's law of cooling, where you heat up a glass of milk and then you let it cool to room temperature. So in today's lesson, we explore some of the more advanced differential equation applications where the area that we're exploring is sometimes called logistical growth. Sometimes it's called bounded growth. It's actually quite a good piece of theory to use in light of the coronavirus, the COVID sort of outbreak. In sort of, it's a very good, simple way of applying with the context of COVID, right? Where you have some sort of outbreak and it grows exponentially and then sort of caps off as, the growth of the outbreak sort of gets capped off with vaccines, etc. So I reckon, I said to my class last year that it'd be quite a popular choice in exams. Was it to be? Maybe it's this year, right? So let's begin. In terms of the theory, I'd like to sort of rehash some of the ones we did previously. So if I said to you exponential growth and decay, and in brackets uninhibited, so unrestricted, right? Yeah, we had the formula where the differential equation started off where it equals to some sort of function where it's Kp, where K is a constant and P is the variable that we're exploring the rate of change of. And when you get that, the solution or the actual equation itself is always going to be an exponential, right? And I mentioned this in the last video. If K is positive, exponential growth. If K is negative, exponential decay, right? So that's pretty straightforward stuff. Nothing too fancy there. We covered that in the last video. Now, we then also covered modified growth and decay. And for a lot of schools, this is going to fall into the extension 1 syllabus, right? Where the modified basically has it starts off with a different differential equation where it's K, P minus, sorry, maybe I'll use B minus P, right? Where B is some sort of room temperature, some sort of constant, right? Constant room temperature is the most common context. Sorry, I want to put a nice box around this. And then if you sort of integrated that as well, you get an exponential, but you get an add-on there with the constant A, E, and it's almost mine. Now, don't quote me on this, but maybe you can. Most of the past paper questions I've seen for modified growth and decay is always negative K, right? The K is always negative because you're either dealing with the shape of, it's always sort of coming towards the room temperature or the oven temperature, right? It's rarely going to be a positive value of K. That makes it quite interesting, right? That they're the types of questions. I think I've only seen it once or twice where it's a sort of modified growth scenario where K is positive and it sort of steps up and then sort of increases. Rarely the case. Nearly all the cases are with a negative K. Now, that leads me on to the third case, which is what we want to deal with today, right? Where some schools call it logistical growth. Some schools could just call it growth with a maximum limit. So maybe I'll go growth with max limit. And I'll put in brackets here, logistical growth, right? Very topical, right? Because it's, you can use some model viruses and stuff very simplistically, falls into this bucket. So let me give you the formula and maybe I'll prove it after, right? So if I said to you, dp dt follows a formula where it's like K, P. It's almost like a combination of the two above, right? Whereas P times this, right? So it's actually like a parabolic a quadratic equation there. Now, what's important here, there's a few variables, right, that we need to sort of call out, where obviously K is a constant, right? But more importantly, N is also a constant, but it's the max limit, right? So also a constant, right? And the variable P, I mean, I don't need to call it out, but that's the variable that we're finding the rate of. Now, what you want to prove this to look like in most of the questions I've seen. So let's be honest, we've had 2 years of past papers with these ones here in New South Wales. The ones I'm going to show you, the formula I'm going to show you is the most common way that they want you to express. So make sure you can prove it in this form. Yeah, but sometimes it might look a bit different, but most of the times it looks like this: BE minus NKT. All right, so a shape that looks like that, where, once again, in this case, B is a constant, right? Now, what you want to do, right, the thing that helps you break this question, right, the intensity of this question is basically the ability to integrate from this part to this part, right? That is the key. Now, if you're doing extension 2 4-unit maths, you can actually integrate this without any hints. However, you're not, right? In context of this lesson, it's an extension 1 3-unit lesson. So what you actually need, and maybe I'll use a different color, I'll use green, to basically illustrate, there is one little thing that I need, right? That gets me from here to one little box, and that little box, maybe I'll do it down below. So note, this one's key, all right, to help with the integral, because it's very hard to use differential equations and integrate, but I will need this, right? Now, 1 over P, N minus P, right? You have to be able to prove this green box, right? Equals to 1 on N, 1 on P, plus 1 on N, minus P. Now, why is this green box, why is this green PC so important? Because this is the reality, right? This is the reality. When you make differential equations with this, when you turn that into something that's a differential equation where you put all the things with P's on one side, so you can see P, N minus P as a bracket, goes to the side and becomes a reciprocal. dt comes up with K. You can integrate the right-hand side quite simply. On the right-hand side, if you're trying to integrate 1 on P times N minus P, that's hard, right? That is essentially this bit here. Now, unless you do 4-unit maths, it's very hard to do something like that. So what they do is they help you by going, well, this fraction actually looks like this. If you can sort of, part A, most questions prove that, you can actually integrate this bit, because if you think about it, the 1 on N is constant, so you sort of take that out from the integral. 1 on P, that's as Ln if I integrate it. 1 on N minus P, that's linear. I can integrate that with Ln. So the key is to basically, whenever you try to start this question, use a green box and so that you can have expressions that you can integrate, right? And just to be absolutely clear, to prove the green box, obviously start from the right-hand side, because there's 2 fractions, common denominator, put it together, and you'll prove the left, right? That's the theory. So you know what? Instead of me proving this to you and then doing an example, let's just hit a past papers, because I'll do 2 past papers that basically illustrate this concept anyway. So, and hopefully through those 2 examples, past papers, you'll see how this sort of comes to bear, right? So the first past paper we have is from Kalara. Yeah, so you can see, look at this question, right? What a classic. A disease is spreading through the population, COVID, at a rate proportional to the people who have it and the people who do not, right? So actually, in the question itself, the differential equation is proportional to the people that have it and the people that don't, right? That's basically what this represents, right? And it's represented by this. Cool. Yeah. Now, can you see simplify? So this one, they don't actually tell you to prove it, but that's, simplify means the same thing. Yeah, because that's going to help me integrate, right? That's going to help me integrate. And then B, hence solve this. Now, what do they mean by solve? They want me to prove that P equals to that exponential equation, 3 marks, right? 1 mark for that, 3 marks for that. A classic question. Now, the next question I'll show you is a bit more parts to this, right? A few more parts to this, but this one here starts off like this. Let's start. So part one. So they want me to simplify. So normally, right, what they're asking me to prove here is basically simplify this to an expression that would then help me integrate, right, the differential equation. So common denominator of that. In this case, the k, I believe, is going to represent the maximum growth, and I'll show you a graph later what that, what the shape of this looks like. So guys, common denominator that k minus p plus p, beauty, because then the p's cancel out, and you get k, which is a constant on top of p, k minus p. Right, great. That's my answer. Yep, piece of cake. All right, that's 1 mark. Part two. Now, part two, hence or otherwise, solve that. So we're going to start off with this differential equation, right? We're going to start off with this guy, 1 on 25 here, p times 1 minus p on. Now, I'm not a fan of fractions. The very first thing, I'm going to get rid of that 1,000 there. I'm going to common denominator inside there. So it becomes 1 on 25, p 1,000 minus p over 1,000. Yeah, now, this is what I'm going to do. So this is dp dt, yeah? With all differential equations, right, we're basically going to say, the dp, p, 1 minus p, they all come to the same side. The dt and the constant, they all stay on the same side, right? So let's leave the 1 on 25 times 1,000, so 1 on 25,000 on the right. dt comes up. So I want this guy up here, and I want this sort of down here, right? Let's see. So I got 1 on p times 1,000 minus p. Now, automatically, you can sort of see that the p times 1,000 minus p is the same as p times k minus, the k in this case is 1,000, right? Yeah, k is 1,000. You know what? I'm going to, just because the question leads me here, see how in the thing I proved up here, see how there's a k here? Now, you don't have to do this, but k and the k there, so 1,000 is obviously k. It looks like they've taken this 1,000 and they've moved that over as well, because then the 1,000 comes upstairs. And then it sort of matches part one, right? So then that's k, that's p, k minus p. That's nice. I can use that replacement in a fairly switched manner. So then the 1 on 25 is the only thing that's left here, and then dt, right? Yeah, I just looked at the question and I said, well, let's use part one by having the k on top. Beautiful. Cool. Now, once you get down to here, it's quite a simple case of integrating both sides, right? Now, like I said, I can't integrate this, easily, but fortunately in part A, I can see that by k, if k was 1,000, then I can replace that blue part there with the two fractions, right? So I can integrate them because they both fit within the ln integral quite nicely. Let's have a look. So that becomes, was it 1 on p plus 1 on k, which is 1,000 minus p dp. So just be absolutely clear, where did I get this from part one, right? Part one says if I have k on p times k minus p, I get that, right? Beautiful. And then on this side now, I'll do it all at the same time. So 1 on 25, that's a constant dt. All right, let's do it. Let's do the integral step. So now integrating 1 on p, ln p. Normally I'll put absolute values, but because p is, it's a population, always positive. Let's leave it as p. Plus also, we know that 1,000 is the highest number that the population go to, right? So then this one doesn't need it. You can put the absolute value in, but it makes no difference. Oh, sorry, for this one, just gotta be careful. I say I was minus p on the bottom, right? I need the derivative of it on top, so that becomes -1, which means in front of here I need a negative. So when I actually do this, it becomes a minus over here, right? Just be very careful. So I'll put in pink, it becomes a minus ln of 1,000 minus p. You can't use absolute values. I mean, it doesn't add anything, that's all. this guy's t, and then plus c. Now, it's important for you to identify if there's two integrals on both sides, you only need one constant. It's almost like the sum of all constants, right? Cool. Now, does it tell me how much my population starts with? Let's see. When t is 0. Right. Let me just see. Nope, doesn't. That's fine. So I can't find. So normally, right, if this was a numerical question, they might give me a value to find c, right? So when t is 0, p is something. In this one, they don't. So I'm just going to carry on. Let's do this, right? Let's carry on. Guys, what am I trying to do? I need to make p the subject. That is the key. So let's utilize some algebra to do it. So let's combine my logs here. All right, that's like p on top. 1,000 minus p equals to, let's just go t on 25 plus c. Guys, exponential and logs are mutually inverse. So I'm going to exponential there and almost exponential that. Right, so then e of ln goes away and I get p on 1,000 minus p equals to exponential on t on 25. I'm trying to write this neat but small, 25 plus c. Yeah, now, almost there, almost there. So what I'm going to do, I'll just copy and paste that up here so I can carry on with my algebra. Now, before I do anything, I'm just going to be smart about this, right? Just to clean up my algebra, because I'm going to times this up, and so I'm going to do this if that's okay. I'm going to replace. So I'm going to break this guy up. Yeah, I know that this guy's the same as e t on 25. You know, like when you add something in the indices, it's like times. Yeah, like that. And then I'm just going to replace this with a capital A. Yeah, so then it becomes like equals to a times e t on 25. Yeah, where a equals to e to the power of c. Yeah? Now, why is that okay? Because c is a constant. If you take e to another constant that you don't know yet, I'm just going to let that be another constant, right? Which is capital A. Yeah. At this point, right, you got to understand that capital A, in the formula that I gave you before, there was capital B. You'll see why in a second, right? So let's just carry on, and you'll see why there's a capital B in a second, guys. Let's times this guy up now, right? Times it up upstairs, all right? Let's see what you get. You get P equals to A E T on 25, 1,000 minus P. Now, obviously, then I'm going to use rainbows to expand this, right? Or just expand. Some teachers say, and then I'm going to. Can you picture this in your head? So I'm going to expand. There's going to be a term with P, and then I'm going to throw it over the fence and combine it. So hopefully, can I do two steps in one? So I get P, and then when I expand it, right, the second term is going to have a P in there. I'm going to plus it over. P A E T on 25 equals to 1,000. Said 1,000. Wrote 10,000. A E T on 25. Great. Now, I need to make P the subject, so I'm going to factorize a P out. All right. Let's see. Almost there. So P 1 plus E. Ooh, A. Left a space for it. T on 25 equals to 1,000 A E T on 25. Almost there, guys. And then divide this bracket over, right? So therefore, now you can leave your answer like this. Right, and it's perfectly fine, perfectly fine. However, some teachers don't like it, right, because it's not simplified or it doesn't look very neat. And that's perfectly fine as the right answer. Now, what we're going to do is last piece. I'm going to divide. Can you please divide everything by A E T on 25? Right, divide both top and bottom. Right, divide this, and divide this. Right, look what you get. You get therefore P equals, when you divide the top, you get 1,000. When you do now 1 divided by this, you still get like 1 on A, and then E, because you're dividing the exponential, becomes negative T on 25 plus 1, right? You get that? That's nice. Now, guys, this is the sort of final piece of the puzzle. Ooh, let me just check that my formula here. Yep, perfect. Had it. Yep, just check. So then all I'm going to do for the final piece is I'm going to replace the 1 on A, with with the letter capital B, and then you have it, right? Then you go, and then just switch the order. So you go, therefore, P equals to 1,000, 1 plus B, E minus T on 25. Perfect. Now, what I'm going to do, while I put a box around this, I want you to see that structurally, yeah, and then you can say over here where B equals to 1 on A, yeah? Done. And that's the answer. Now, can you see structurally, 1,000 on 1 plus B, E minus T on 25 looks very similar. In fact, it looks identical to that, right? Exactly the same. The only difference, N is 1,000, right? And K is 1 on 25. Yeah, so, oh, sorry, yep. Yep. Yeah, so that's my answer. Let me just scroll down so you can see it again. Yeah, actually, I think K would be 25,000 and then multiplied by 1,000. So then it's 25. Yeah. So then this is the structure that they want the answer in. Now, can you leave your structure like this one? Absolutely. That's fine. Unless the teacher says, can you please prove something that looks like the blue box there? I think both of them are fine. That's how you do it. Yeah, stock standard. Let's do another question that has this sort of structure. So all you got to see at the start is that to facilitate your integration in 3-unit maths, you need to have this proof, right? That integration step requires you to have that step because it's very hard to integrate one on something that is a quadratic. We split it in 4-unit maths. It falls under a topic called partial fractions. We don't have that in extension 1, so we needed something, and part 1 is that something. Let's try again. Let's give it another go. So this was in ASCM 2000. Same deal. Now, I like just to be sure, just to give you. If I go back to the theory part of this, right? If I was to draw a quick sketch of what the shape approximately looks like, right? What logistical growth looks like is that there's a picture like there's like a start, right? Here's when time is 0. Yeah? And this is like population of the virus, population of animals, blah, blah. It starts off with something. And this is like N, right? The max, it's sort of the max number. Let's say in the next context, you'll see that on an island, the population growth of a certain animal sort of increases exponentially, but because the island is limited, the resources are limited, the population sort of caps off, just like coronavirus potentially, right? So it sort of goes like that exponentially, and then it sort of exponentially sort of flattens out, right? Sort of like a double exponential as part of the context, right? So you'll see, let's do one more question on this where the population, from the ASCM question, the population of 1,200 feral cats. So it's in done point, the rate of change is this, population, see structurally the same thing where it's P times something with P. All right, now look at the classics, right? Classic 1 and 2, 1-2 punch, right? Show, solve, right? Solve that, and then 2 more, right? 2 more sort of gimmies, right? Find the limiting population and how many months for population to double, right? So like how many months, that's a time question. So part 1 and 2, exactly the same as before. In fact, exactly the same marks, right? Part 3 and 4, just 2 more marks just to use the equation that you derive, right? Exactly the same process. Actually, slightly different because part 1 that hit for this question actually says show. So it actually gives you what you have to prove, right? Makes it a bit more straightforward. So you can see I'm proving a statement. Be smart about it. It's easier to prove from the side with the double fraction. So 1 on P, 1 on 10,000 minus P. Guys, we are going to common denominator that. Where 10,000 minus P plus P, just like before, P's go away and then you get exactly what they want you to get. 10,000 on P, 10,000 minus P, which is the left-hand side. Done. Yeah, 1 mark there. And then we go about it. If you've done this, 3-4 times leading up to an exam, it should be automatic, right? It should be fairly automatic. So we start with the differential equation. right? P on 30, 1 minus P on 10,000, right? Once again, I'm not a fan of the fraction. So next step would be common denominator, the inside there. So you get P 30, 10,000 here. It's also important because then you get something that resembles what you've proven in part 1, right? Look at this. So once again, let's create our differential equation where, just like before, dp, that guy's going to come over, that guy's got p, and I'm going to bring the 10,000 over so it looks like part 1, right? It looks like this green box here, you know? It's just looks like this green box here, yeah? So bring that over, and then the dt and the 30, 1 on 30 is going to stay on that side. So everything over, so this guy times this guy downstairs, 10,000 over, so 10,000 over p times 10,000 minus p dp equals to 1 on 30 dt. Yeah, exactly the same as before. We know, right, that this utilizes this box, right? Yeah, utilizes that box where I'm going to replace. So I'm going to integrate both sides. But before I do that, I'm going to replace that blue with the 1 on p plus 1 on, yeah, to make it integratable, right? Integral of 1 on 30, that's constant dt. Exactly the same as before. So let's do this, right? Bit of pace. So that becomes ln. Once again, p is positive plus, and we know p is less than 10,000, that's, or minus, right? Remember, just like before, we need a minus here because p is minus there. It becomes a minus there, so that becomes a minus ln 10,000 minus p equals to 1 on 30 t plus the constant. Now, did I give me information in this one to find the constant? I do. Yeah, just to be absolutely clear, there it is there. So when t equals 0, the population is 1,200, right? We're going to sub that in to find. So in this case, you don't need the capital A, capital B stuff, right? Because they give you information to find the constant. Right? So once you get to a point where you're comfortable to sub it in, we will. And I think that point is right after this step. So minus p equals to 1 on 30. Oh, let's call it t on 30. Must be amazing. T on 30 plus c. Yeah. This feels like a good point to sub in to find my constant. So, you know what? Can I ask? I'm just going to save a bit of space. I'm just going to pop over here a bit. So when t equals 0, the population is 1,200. If you sub it into there, it becomes ln 1,200 on 10,000 minus 1,200 equals to 0 is gone. C. Yeah, so you sort of get like C equals to ln. What's that, guys? 12,000 on 88,000. No, 8,800. 1,200 on 8,800. Cancel. 12 on 88. What's that? 322. Perfect. So therefore, C equals to ln 3 on 22. Yep. So I could plug that in, right? I could plug that in. So replace the constant there with this guy. Just to clean up your mass, right? Clean up your mass. ln 10,000 minus p equals to t on 30. And what's going to happen is when I plus ln 3 on 22, I'm going to bring this guy and combine it with that ln. Yep. Let's do that. So let me just shrink it a bit. Yep, let's do that now. So, you know what? I'm going to copy that so I can work with it up here. Hope I can fit it. It's a bit longer than the previous because it's a constant, right? So when I move it over, it becomes a ln. Yeah. I'm going to, you know what? I'm going to leave it. Maybe I'll leave it. I'm going to leave it there. I'm just do what I did before. Let's just exponential both sides, right? Because then what I'm going to, if I put it there, combine it, and then when it's going to go back over the other side anyway, so I can leave it there. All right, 10,000. Yeah, P equals to E of this guy. Now remember, plus is like times, right? Plus is like times E of this guy, E of ln goes away times that, right? Exponential and this guy cancels out. Is that all right? Because when there's a plus, you can actually split it like I did before with the times in between. E and ln then mutually inverses each other out, 3 on 22, right? So you get that as a constant in front. So before, that number there would have been A, but now it's 3 on 22, right? So same thing. So I time this guy up just like before. So it becomes like 3 on 22, E, T on 30, 10,000 minus P. Remember, can you do me a favor? Keep this in your head. You know, before when I divided everything by A, E, KT, whatever that was, right? This one, I need to have the final answer to have a negative exponential, right? That's how you get your limiting sum, which is the next question. You need the negative exponential there. So keep that in mind. Now, what I did before was I used rainbows here, where I'll bring this, can I do sort of like 3 expand, move, and factorize all in the same step? Let's be amazing, becomes 1 plus, right, when this goes over 3 on 22, T on 30, equals to 10,000. That's like, oh, can I just put as 30,000 for now? 22, yeah, I know that simplifies, let's not, because it hurts my brain later when I try to simplify it, and then divide that down. So you can leave it like this, but that is massively ugly. So please don't leave it like this. ET on 30. So what I did before at this step was then divide everything by 3 on 22. That's A, and E, K, T. Actually, that's NKT, right? Yeah, NKT. So then you get therefore P top. Now, if you divide by 3 on 22, that becomes, what's that? 10,000. Yep, 10,000. Everything else goes, right? So 10,000, which is great because that's N. And then now I'll rearrange the order. Yeah. So there's 2 terms on the bottom. There's a 1 and this guy. I know the second one becomes 1 because that's what I'm dividing by. And then 1 on this guy, so reciprocal of that, 22 on 3. And E minus T on 30, which is my answer. Sorry, I just freestyled that. Let me just check my answer. Perfect. Perfect. Yeah, they sort of simplified a bit more, but I'm going to leave it. Yeah, that looks good. They simplified by getting rid of that fraction on 22 and 3. This times even by 3, right? What is? Right? Looks good. Looks good right now. How's that? So part 2, 3 marks, boom, right? And then 2 more marks. So they're just going to use that formula to do it. So what I'm going to do, let me just copy this to the next slide. We do a bit of PowerPoint cleansing. If you'll let me, there you go. Come on, PowerPoint. There you go. Well done. Microsoft there, working. Yeah, it's already grouped that for me, which isn't good, isn't cool. So I'm just going to right click and group that. I can sort of cleanse a bit more. Cleanse that. All right, guys. I'm going to start here. My classes hate it when I embark on my PowerPoint cleansing. There you go. Hence, find the limiting feral population. So limiting, right? The moment you see the word limiting in all these sort of exponential growth contexts, they basically, they're referring to T goes to infinity, right? So when T goes to infinity, what happens to P, right? The beauty about this is when exponentials expressed as a negative value, this guy here, yeah, when T goes to infinity, right, when time up there goes into infinity, that's like E to the power of negative infinity, which means E minus T on 30 goes to 0, right? Because E to the power of negative infinity heads towards 0. So this thing goes to 0. So therefore, P equals to 10,000 over this bit 0, right? 1 plus 22 on 3 times 0, that's just 10,000, right? In other words, if you remember the graph that I drew, right? If the highest one there is N, or in this case, 10,000, as the population increases, right? As it goes to infinity, it'll head towards that 10,000 mark, which makes sense, right? Contextually, 10,000 is the right answer, right? 10,000 is right. I'll leave the graph up there. So if your teacher doesn't sketch you the graph, they're missing a beat because it gives you a depiction of what this question is all about. So, right now we've done 3 cases of exponential growth and decay. The first one, exponential growth, exponential decay. There is unbounded growth, and for decay, it sort of goes towards 0, right? Second case, the growth, there is no growth, it's just decay. But basically, the decay is such that there's room temperature, right? In which case, the thing that's heated up cools down to room temperature. If it's an oven temperature, it will heat up to oven, right? That's the shape of the graph. It's an exponential graph. Logistical growth starts off exponential and then plateaus, right? With maximum cap. So it works really well in context of population growth on an island that's restricted, or in a lab, or it's coronavirus with people getting infected, but then because of the vaccine, they there's only a limited number of people that can get sick, and then sort of plateaus out. Very good context in light of all our COVID questions. I reckon it's going to be a common question. All right. After how many months does it take for the population to double? So population double there is key. All right. So in other words, here we're talking about 2p, right? So when the population 2p, I'm going to sub that into there. No, that's not what I want. Population double, right? Not 2p. Boom, boom. Right now, it's 1200. I want p equals to 2400, right? That's what I want. Yeah, that's what I want. Because I know what the initial is. So I'm going to sub p 2400 into there. So 2400 equals to 10,000. 1 plus 22 on 3e. And then I have, it looks messy. It's just an exponential equation. Swap this guy and this guy around, these 2 elements. Swap them around. So you go like 1 plus 22 on 3, e minus t on 30 equals this guy on this guy. Yeah, I know that simplifies for now. So this is what I'm going to do. For now, I'll just leave it there. Minus 1 over times 322. I'm just going to manipulate it to a point where I get it, right? So if I go e minus t on 30 minus 1 times a 3, so 3 on 22 there. This guy minus 1, right? Log both sides, times the 30 up, divide the negative down, boom, right? Whatever this is on your calculator, right? Whatever that is, you're going to get t equals to ln on this guy. I'll simplify that in a sec, right? Just so bear with me. I just want to show you the working out. And then, so that's like negative t on 30. If you times the 30 up, minus 30 there. Yeah. So if you had to punch this in your calculator, you can do it there, or you can simplify everything. The negative sort of reciprocates that, right? And so you get like 30 ln 44 and 19, I believe. Yeah, you might want to check that. And that time there is 25.19, blah, 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 blah. So it looks like, how many months does it take for the population to double? Looks like it takes, now, to double, so if you wrote 25 months, it won't double yet. 26 months will double. So it depends on that. I think it's unclear, it's vague. Maybe for this one, let's round it down, 25 months. Yeah, hasn't yet doubled, but it doesn't say how many months, what's the least number of months for the population to exceed the double, right? It doesn't say that. So you can do 25 months. Let me just check the answer. The answer says nearest month anyway. So there you go. Vague question. Guys, that's logistical growth, right? So the key is to be able to do part 1, where it's a simple proof, common denominator, and then use that as part of your integration, right? Hope you enjoyed that video. Please, if you haven't already done so, like the video, subscribe, tell your friends. I'm doing this for free just to give you a bit of theory and examples, past paper questions for the syllabus. Hope you enjoy that. I'll see you guys later.